Okay, so in the last video we started talking about 4.3, which is called wave characteristics. And the main thing we talked about in the last video was about the difference between the wavefront and the array way of looking at a wave. And we also talked about wave intensity, and intensity being inversely proportional to the distance from a wave source squared, and also proportional to the amplitude squared. Okay, and so in this video we're going to finish up this unit, or at least start finishing up this unit by talking about the last two wave characteristics, and that is superposition and polarization. Now, both of these are important in their own right. I'd say between the two, superposition is probably a little bit more important, or at least it will be in the next unit that we're going to do. But polarization is one of the more abstract concepts, and so we're just going to kind of start talking about polarization in this video, and then we'll do calculations in the next. Okay, and then we will be done with this unit, and we'll be getting ready for a test. Once we're done with 4.3, not in this video, but probably the next video, we will be done with this unit and ready for our first waves test. So let's start talking about wave superposition. Okay. And so I will briefly explain the concept of wave superposition, and then I've got two videos talking about wave superposition that I want you to watch. And again, this is one of those things where the concept, we're just kind of talking about the basics here in 4.3, and then we'll go into kind of more detail in 4.4 and see what we can do with wave superposition. Okay, but the basic idea of wave superposition is if you have two objects that are made of matter, we know that when two objects collide, they they collide, they bounce off of each other. You know, think of like two cars crashing into each other, or a pool ball hitting another ball. They bounce off of each other. Okay, there's some type of collision. Now, waves are not matter. Okay, waves transfer energy but not matter, and so when they meet up, they behave differently. And so it turns out that when you actually have two waves meet each other in space, you get what's called superposition. Okay, and superposition kind of gets its name from the word superimpose, to kind of like layer things together on top of one another. Okay, so wave superposition is basically the property that waves have, whereby when they meet each other in space, their displacements add together algebraically. And in that one sentence, we have what wave superposition is. Okay. Again, wave superposition is just a principle whereby when two waves meet in space, their displacements add together algebraically. Now, let me explain what that means. Of course, when we say displacement, remember displacement is not the same thing as amplitude, because amplitude is maximum displacement from equilibrium. And a wave, if you imagine a transverse wave in your mind, its displacement goes up and down, depending on where you are along the wave. Okay, so when one wave meets another wave, each wave has its own separate displacement, and algebraically just means, well, I guess in simple terms, that you take into account the sign. So for example, if two waves meet and one of them has a positive displacement and the other has a negative displacement, you would basically be adding a positive number plus a negative number. Okay, so you'd be subtracting. And so that is the idea of superposition. And it's a very easy concept to explain. It's not always the easiest to do problems with. As we will see in the next unit, because waves have this property of superposition, they can experience what's called interference, constructive and destructive interference, and we'll talk more about that in the next video. Okay, for now, I'm going to link these two videos below so you can watch those videos and learn more about superposition. Okay, so just to look at a few examples of superposition. Okay, in the simplest terms, you can imagine if you have two wave pulses going towards each other. So here we have a red pulse going to the right and a blue pulse going to the left. When they meet up and occupy the same place in space, they kind of add together. Right? In this case, they both have a positive displacement, and so if you add a positive displacement plus another positive displacement, you get a bigger positive displacement. Okay, so this is an example of what's called constructive interference, and again, we'll talk more about interference in the next unit, but this is possible because of superposition. Again, just the idea that waves add together algebraically, their displacements add together algebraically when they occupy the same point in space. Now, problems with superposition could have to do with interference, or they could just be general superposition problems. So let's take a look at some examples of what that might look like. Okay, if you're still unclear with the concept of superposition, here's the idea. Let's say you have two waves, wave A and one wave B, and let's say they occupy the same point in space. Okay, somehow they meet up in whatever way. It could be electromagnetic waves, crossing paths. It could be water waves colliding with each other. Okay, it doesn't matter. Okay, so we have wave A and wave B, and superposition says that when they occupy the same point in space, their displacements add together. So fundamentally what that means is if I take, for example, this first point, if I want to find the superposition of wave A and wave B, I would take this point that has a displacement of 0, this point that has a displacement of 0, and so my superposition would start with a displacement of 0. And then I would go to the next point. Wave A has a displacement of 1 right here. Wave B has a displacement of 2 right here. And so the superposition of those two would be 1 plus 2, which is 3. And so on and so forth. This would be 2 plus 0, which is 2. This would be 1 plus, notice that here wave B has a displacement of negative 2. Okay, so 1 plus negative 2 is negative 1. That's what the algebraically means in the definition. Okay, that you take into account the sign here. Okay, this has a displacement of negative 2, and that has a displacement of positive 1. And then you would just go point by point like this. 0 plus 0 is 0. Negative 1 plus positive 2 is positive 1. And you would just go point by point like that. And if that seems kind of tedious, it really is kind of tedious actually. And so you don't too often get points or questions on the IB exam where you have to do superposition graphs by hand, but it does happen from time to time. I have seen questions asking you to actually sketch the superposition of two waves given the two graphs, and so it's not hard to do it all. It's maybe kind of time consuming, and also sometimes you get a graph that doesn't look like what you expected. So for example, here we clearly have two kind of sinusoidal looking graphs with the different frequencies and different wavelengths, but they have the same basic shape, right? Kind of like a sine graph here and a sine graph here with different wavelengths. But when you take the superposition of the two, notice that what you get is not really sinusoidal. It's kind of like a wonky type of periodic function. Okay, it's not symmetrical, is what I'm saying. Okay, so when you have superposition of waves, the resultant, the superposition can kind of look kind of weird, especially if you're adding more than two waves. Technically speaking, you can have superposition of an infinite number of waves. Okay, so let's go to the next example. Okay, this is maybe a more basic example. It says the diagram below shows two wave pulses A and B traveling towards each other. Sketch what the resultant wave will look like at position AB. That is, when the two wave pulses are overlapping. Now, because of superposition, at point AB, we know that we're basically going to have this wave here, plus this wave here. This wave on the left has a displacement of positive 0.05, and this wave pulse over here has a displacement of negative 0.15. Again, the sign is important. It's negative because it's below where the 0 line would be. Okay, and so if this was a multiple choice question, you would just do, 0.05 plus 0.1 or negative 0.15, and you would get negative 0.1. Okay, so the answer would be 3. Just a real basic type of problem there. And in the next unit, when we talk about interference, we'll see that's an example of what's called destructive interference. Okay, just look at another example that's basically the same type of example. They're just going to cancel each other out. Let's look at some IB questions. Okay, this is a really easy IB question actually. The wave pulses travel along a string towards each other. The diagram shows their positions at a moment in time. Which of the following shows a possible configuration of the pulses at a later time? Okay, now clearly we know that when the two waves meet up, because they appear to have the same amplitude, but one has a positive displacement and one has a negative displacement, when they completely overlap, you would expect them to cancel out. And that's an example of what's called destructive interference. And so that would correspond to answer choice C, which is in fact the correct answer. The other ones are not possible, and the reason is after the waves pass through each other, what's going to happen is this pulse up here, okay, this positive pulse up here is going to be on the left side like this, and this negative pulse, once it passes through, this pulse is going to be kind of over here. Okay, they're just going to pass through each other and then keep on going. Okay, and none of the other answer choices show that. D basically has the opposite of that. And A and B, the issue with A and B is A and B would only be possible if one of these had a bigger amplitude than the other. Okay, as it is, you can tell just visually that they basically have the same amplitude because one is not necessarily bigger in size than the other. So the answer there is C. Okay, and just one more quick example. Two waves P and Q reach the same point at the same time as shown in the graph. The amplitude of the resulting wave is what? Now you have to be really careful with the terminology. Amplitude and displacement are not the same thing. It's really important that you understand that. If you're not clear on the difference, let me give you a specific example. If you look at these graphs, these waves both have an amplitude of 1. By definition, amplitude is the maximum displacement from equilibrium. The displacement of the wave, though, changes along the graph. For example, right here, the displacement of this wave is 0.5. Right here, the displacement is 0. Right here, the displacement is 0.5 again. So don't confuse displacement, which is a variable, with amplitude, which is a constant. Okay? This is asking about the amplitude of the resulting wave. So in other words, if you did the superposition of wave P and wave Q, okay, the amplitude of that superposition, what would it be? Now, this particular question was done as a multiple choice question. And so let's kind of try to reason this out. Okay, the easiest way to do this is just to pick some random points and go from there. So let's start at 0. At 0, the superposition of P and Q would be positive 1 plus 0. And so the superposition would be at 1. Let's go to another point. Let's say this point right here. This point right here appears to be approximately 0.7. Okay, and 0.7 plus 0.7 is 1.4, and so the superposition would actually be up here somewhere. Okay, let's go to another point. Okay, let's see right here, 1 and 0. Okay, so the superposition there would be 1. And you can keep going along like this, but basically what we have here is we have a local maximum. In other words, the graph peaked right here at 1.4 millimeters. So the amplitude of the resulting wave is 1.4 millimeters. Okay, and you can use process of elimination to eliminate the other ones. Okay, 0 amplitude would mean complete cancellation the entire time. We already have a non-example of displacement bigger than 1, so B is out. And the only way that we could get an amplitude of 2 is if we had these two waves meeting and they were perfectly in sync, so that at that point in space the superposition was 1 plus 1. And because there's a phase difference between these two waves, that's never going to happen. Okay, if these two waves had a phase difference of, let's say, 0, then they would completely overlap and D would be possible. But as it is, C is the correct answer. Okay. All right, so here is an IB question. try to answer this question on your own. This would be a 2-mark question on the IB exam, so try to answer this question in complete sentences and see if you can get the 2 marks. Okay, so the question says, outline what is meant by the principle of superposition of waves. Here's what the IB gave marks for. Okay, 1 point for mentioning when 2 waves meet the resultant displacement. Okay, so just stating the fact that superposition has to do with the fact when 2 waves meet, it has to do with the resultant displacement of those 2 waves. Resultant is just another word of saying net or overall. Okay. The second point is you had to mention that it's the sum of their individual displacements. You had to specifically use the word displacement to get full marks. Okay, you didn't have to say vector sum. Okay, if you said algebraic sum, that would be fine. But it is technically the vector sum of their individual displacements. Okay, really all you had to say was sum, though, to get full points. Okay, so see if you would have gotten those 2 marks, and if not, make sure you're answering the question in complete, coherent sentences. But that's basically it as far as superposition goes. Okay, and just to kind of tease you, if you're ever going to science or engineering, you'll learn about what's called Fourier series. Fourier series is basically the idea of a Fourier series is you can take any function you want and express it in terms of an infinite number of sine or cosine waves. Okay, so for example, if you take, 1 sine wave and you add another sine wave and you add another sine wave, each of these with a different frequency, and you keep going, you can get some weird funky signal like this green line represents the superposition of all 5 of these waves. And you might think, why would you ever have to do that? Well, because in real life, a lot of things are not perfect sine or cosine waves. They are funky like this. Like imagine talking on the phone, your voice, the modulation of your voice looks like some weird thing like this. And so basically the way that information is transmitted digitally is it's broken up into this infinite sum of sine and cosine functions, each one with a different frequency. Okay, and again, that's called a Fourier series. If you ever want to learn more about that on your own, it's a really interesting concept, and it's also used in digital signal processing and stuff like that. Okay, so that's just kind of a teaser, and that's basically it for superposition. Okay, now the last thing I want to talk about, without getting into calculations, is the concept of polarization. This is one of the more conceptually difficult ideas in this unit. I will do my very best to explain this to the best of my ability, but I would highly encourage you to make sure that you work on your practice problems, you read your textbook, and you do the practice problems in your textbook as well. Okay, so polarization, this is the end of 4.3. So here's the idea of polarization. Okay, polarization, first of all, you can only have polarization for a transverse wave. So when we say a transverse wave is polarized, what that means is it is only allowed to oscillate in a certain direction. Okay, it is only allowed to oscillate in a certain plane. Okay, so remember, in a transverse wave, by definition, the oscillation of the particles are perpendicular to the direction that the wave is moving in. Okay, so something like this. That's a transverse wave. Longitudinal waves, on the other hand, the direction of the oscillations is parallel to the direction of motion. That's the difference between a longitudinal and transverse wave. Now, transverse waves can oscillate in basically an infinite number of directions. And just to kind of give you a visual, normally I would show you this like physically in class, but I can't. If you imagine, for example, let's say you and a friend have a jump rope, and each of you holds an end of the string, and you kind of move your hand up and down, and you make a wave kind of like this top wave up here. Okay, that would be one way to oscillate that rope. Okay, but you could also move your hand side to side. Okay, rather than up and down, you could go side to side. Or you can kind of go diagonally, and you can go diagonally at any one of an infinite number of angles. Okay, and so that's what it means when it says transverse waves can oscillate in essentially an infinite number of directions. whereas longitudinal waves don't have that ability. And so because of this, polarization only applies to transverse waves. Okay, here you can see on the green, those are just two of the infinite number of possibilities of a transverse wave oscillating in a given plane. Okay, so you can see the red one is going up and down, the green one is going side to side, and you can have any number of infinite angles in between that. And so polarization, if a wave is polarized, is restricted to oscillate only in a certain plane. Okay, now we're going to focus our attention on the polarization of light waves, or specifically I should say electromagnetic waves. Now technically you could polarize any type of transverse wave, but we're mainly going to focus on electromagnetic waves because that's the most interesting. Okay, so just to recap, light is a transverse wave. It relates to transverse waves, and there's two components to it. There's an electric field component, and there's a magnetic field component. And both of those are oscillating in an electromagnetic wave. Specifically in this unit, we will consider polarization in terms of the electric field being polarized, not the magnetic field. Now, I guess technically speaking, because the two of them are linked, I guess if you polarize one, the other one would automatically become polarized, but the mechanism through which polarization occurs really only affects the electric field. And so when we talk about, this light wave is polarized up and down, what we mean is the electric field part can only oscillate up and down. Okay, so that's basically what polarization is. We're going to mainly focus on polarization of light, specifically the polarization of the electric field part of electromagnetic waves. Okay, so I think that is a good place for us to stop here. In the next video, we will talk more about how polarization is achieved. There's two mechanisms that you need to know about, and then after that we will do calculation involving what's called Malice's law, and then we will be done with this unit. And then you'll have a practice assignment for Malice's law and probably another quiz related to Malice's law, and then we will be getting ready for our test that is going to be next week. As always, please let me know if you have any questions, and I'll see you guys in the next video.